Hi. In my previous video, I had spoken about computational fluid dynamics, its basics. Then we focused on one specific discretization method, which was finite difference method. In today's video, I want to talk about boundary conditions and only boundary conditions. How to use them, how can we apply the different types of boundary conditions for specific cases, a few things to keep in mind while writing your own codes, and that's it. So this is going to be the topic of today's video. So let's get to it then. Okay, let's talk about boundary conditions and specifically what it is. So first thing that boundary condition does to our problem is it makes it a well posed problem. What does that mean? So let us look at it this way. Analytically, if we focus on this equation, a simple conduction equation, one dimensional conduction equation, if we integrate this twice, what would we get? We would get t is equal to c1x plus c2. Now for us to be able to solve this question, or to be able to model this physics, we should be able to solve this equation, but we have only one equation. However, there are two constants in place. Obviously, we cannot solve this unless and until we know the values of these two constants. And why did we get two constants in the first place? Because it was a second order equation. Simple. So for this problem to be a well posed problem, something which can be solved, where we can get unique solutions or solution for that matter, whether unique, whether same, doesn't matter, but we should get some solution. And for that to happen, we need the values of these two constants, c1 and c2. And there is where the boundary conditions come into place. So if I give at least two conditions, right, by using which I can calculate the value of c1 and c2, I can substitute that back into this equation and make this equation a solvable case. Right? And this is what the boundary conditions are all about. Second is that boundary conditions help us capture the physics. And what does that mean? Very simple. If you have watched the first video that I have released the other day, in that for 2 hours I talk about CFD, finite difference method, and I also talk about how CFD is used to simulate real life. And for simulating real life, we need a lot of things to come together. So we need to define the problem, we need to then establish what are the initial conditions, what are the boundary conditions, we need to solve the governing equations. For solving that, we will discretize it and then develop an algorithm by using which we eventually get the solution. Now in this entire procedure, governing equation takes care of the physics. Domain is what we are trying to solve, or the problem that we are trying to solve. The domain is the representation of that problem. But what about the boundaries? What is happening at the boundaries? For that, we can take again a very simple case of, say, a lid driven cavity. For this, I have uploaded the tutorials as well with OpenFOAM. So if we take a simple lid-driven cavity, here, how many boundaries does it have? The answer is 4, 1, 2, 3, and 4. So when I say that the fluid, is circulating inside, the domain is open on one end, there is wind blowing horizontally outside this box, eventually it's going to interact with this boundary and therefore enter into this room. It's going to circle around and then go away. But during all these things, or during this entire physics taking into place, these boundaries are going to interact with the flow. So we need to also take care as to what is happening at the boundary. So hence, for capturing the physics in its essence, we need very dearly to mention what happens at the boundaries, and that's why we require to define boundary conditions. And most importantly, for any CFD simulation to run, we need a stable code, a solvable code. Boundary conditions make that happen. So these are the reasons why we need to use a boundary condition in our CFD code. Having said that, now let us talk about what are the different types of boundary conditions. Let us talk about the types of boundary conditions. There are a lot of types of boundary conditions, but as a new user, fundamentally there are 3 types. First is Dirichlet, second Neumann, and third is Robin. So we have Dirichlet, Neumann, and we have Robin. If I have to give you a plain simple explanation of what these 3 types of boundary conditions are, Dirichlet is when we define a constant value at the boundary. Neumann is when we use a derivative instead of a constant value. And Robin is when we decide to use both Dirichlet and Neumann, not necessarily in this fashion, but a linear combination of them. So let me make it more specific and let me write both Dirichlet and Neumann, a sort of their combination. When you use that, becomes the Robin, and therefore it is also sometimes referred to as the mixed type boundary condition. So again, what types do we have? Dirichlet, Neumann, and Robin. Dirichlet is a constant value, Neumann is a derivative, and Robin is a type of mixed boundary condition where it's a linear combination of Dirichlet and Neumann. It's that simple, and that is what makes understanding the boundary condition very easy, because it's very straightforward. There are different types of boundary conditions. Again, there could be more like a cyclic boundary condition or a symmetry boundary condition. But then as a new user, when I'm fiddling around with the fundamental problems, these never come. So, we'll stick to the basics for now. Probably in the future videos, I'll talk more about these things. But for now, Dirichlet, Neumann, Robin should do it for you. And let us now look at simple problems and see how we can implement these boundary conditions. If you haven't already watched the video on the fundamentals of finite difference, this is a very nice time to pause this, go back and watch the entire thing, and then come back and resume this, because what I'm about to talk will make more sense when you watch that video first. So the problem that we would be dealing with which we can, in fact, easily understand. Let us take one-dimensional steady-state conduction, or even one-dimensional steady-state diffusion for that matter. So that becomes very general. I'll write down the equation. The equation would be d2 phi by dx square, right, plus s, and the diffusion coefficient is equal to 0. So this should be the general equation, or to make it like even more general, we can even write it this way. And then divided by gamma. Now in this equation, if you replace phi by T and gamma by that's conductivity, you have a heat transfer problem. So nothing fancy there. And we know, based on the truncated Taylor series, how we can discretize this particular differential term. For d2 phi by dx square, I can write almost equal to phi I plus 1 plus phi I minus 1 minus 2 phi I divided by delta x square divided by delta x square. And what stencil do we adopt for this? Very simply, if this is phi I would say this is phi I plus 1, this is phi I minus 1. It is that simple, right? Now, what about the boundary conditions that we were talking about before? For that, let us again focus on simple problem of one-dimensional case. So let us take a domain. Remember the steps that we had talked about, the general CFD algorithm. We will say draw a domain, then discretize it in number of points. Here I choose to discretize it in 5 nodes, and here I would say that, say, gamma is equal to a constant value of 10. We can ignore s for now. I can say that there are no source terms, so therefore s becomes 0, and simply that equation becomes d2 phi by dx square is equal to 0, and things simplify a lot. Phi 1 and phi, these are the boundary nodes. Now what do we do with them? That is the question. So let us go with the first case, which is the Dirichlet case, and that is a very straightforward case. So say I assume a value of 200 here, 100 here, and if I decide to do that, I can simply now find out the value of phi 2, phi 3 and phi 4. Then I'm good to go. For that, I simply write down the discretization equation at 2, 3 and 4. And what are those? Pause the video, think about it, resume it back. The answer would be, first is T1 plus T3 minus 2T2 is equal to 0. T2 plus T4 minus 2T3 is equal to 0. We have a T3 plus T5 minus 2T4 is equal to 0. Alright. T3 plus T5 minus 2T4 is equal to 0. If this is the case, what do we get? We simply substitute the values of T1 and T5. How do these equations change? We get minus 2T2 plus T3 is equal to 200, minus 200. Then we have T2 plus T4 minus 2T3 is equal to 0. We have T3 plus T5. Now instead of T5, we can write 100. So we have T3 plus 100, or let me rearrange the terms. So we have T3 minus 2T4 is equal to minus 100. And if I decide to convert into a matrix form, I can write minus 2, 1 and 0, 1 minus 2 and 1, and 0, 1 and minus 2, and this would be for T2, T3 and T4 is equal to minus 200, 0 and minus 100. Now if you simply solve this matrix, you get the values of T2, T3 and T4. Please write down the values in the comments, because this is very easy, and now by this time you should be able to do this very comfortably. And simply you can find the value of T2, T3, T4. T1 and T5 were known due to the Dirichlet boundary condition, and we just now found out the values of T2, T3 and T4. Simple. So this is how you can solve the numericals if Dirichlet boundary conditions are used. If we talk about Neumann boundary condition, things become a little bit, different. Let's talk about it. Neumann boundary condition. Here, the idea is that we, instead of using a constant value, use simply a derivative, which is representative of flux, if you may. So instead of writing simply T is equal to so and so, maybe 100, I will write dt by dx at the said boundary is equal to some flux, some value that will be given. Right? So this is the primary difference. Now let us look at the same problem that we discussed before, and let us take the same number of nodes. Now instead of 100 or at the other end, let us assume there is a heat flux happening at the other end, which is of a value, say 10 watt per meter cube, something of this sense. Now the question would be, how do we deal with this? Because so far we have always gone with the Dirichlet approach, so things were very easy. What about this case? Now here there is a very elegant approach. There is a very elegant approach in place, and you may want to use that. And what is that approach? That approach is called as ghost point method. The idea is that instead of using the existing mesh, we generate a ghost node, right? A ghost node which will not be a part of the physical computational, or rather physical domain, but only the computational domain, which we will eliminate later on. We'll introduce, we'll calculate, we'll eliminate it, so that we can use it as a walking stick, if you may, for getting us to the final solution, as a support. So let us look at it. This would be T1, T2, T3, T4, T5, and now I introduce T6. So this is the idea. There are other ways to do or deal with this as well, but we'll talk about it once we solve this particular case. Now, if you remember, we had talked about the central difference scheme for first order differential terms in the earlier video, which was that if we have f dash x, we will write it as f of x plus h minus f of x minus h divided by 2 delta x, right? So if you notice, we have been doing the same thing, the central differencing scheme, obviously for the second order term throughout the domain. So we would want to stick to that, the second order term, or the central differencing scheme. We want to stick to central differencing scheme for the sake of consistency, and also it is very stable. But when we arrive at the last node, since there was no node here, we used to get stuck earlier. But in the case of Dirichlet, the value is given, so we were saved. But now the value is not given, the flux is given for that. So, and for, to get around that, we invent this fictitious node so that we can apply the central differencing scheme. And how do we do that? Very simple. So dt by dx, in this case, at the very end of the domain, x is equal to L indicates the end of the domain. I would write as T6, and again almost equal to T6 minus T4 divided by 2 delta x. And in this case, we already know the value. We have been given the value, which is what? We have been given some value. What is that value? Think about it. The flux. It's 10. So can we write 10 directly here? Again, pause the video, think about it. The answer is no. Why? Because if you remember the Fourier's law, minus k dt by dx is equal to q, and therefore dt by dx is equal to q divided by minus k. Hence, when you want to solve this problem, you should also ask what is the value of conductivity. Now let us assume that the conductivity is 10, q is also 10. For the sake of it, it may be unphysical, but just for the sake of it, let us assume. So if we do that, dt by dx becomes minus 1, which we may then go ahead and substitute here. And then we can go ahead and solve this. So we can eliminate T6 by writing everything in terms of T6. What has happened is that now we have obtained an equation in terms of T6. Alright, now continuing from what we were talking before, in this case, let us look at the equations once again. At the node 2, right, we have the equation based on the central differencing scheme that we were applying before, which is T2, no, oh, thank you, T1 plus T3 minus T2 is equal to 0. At 3, we have T2 plus T4 minus 2T3 is equal to 0. At 4, we have T3 plus T5 minus 2T4 is equal to 0. And now here comes the beauty. At 5, we have, what do we have at 5? At the node 5, we have this equation. Right? No? Then what do we have? We have central differencing scheme. We simply apply the central differencing scheme because we have a node at 6 now. So we write T4 plus T6 minus 2T5 is equal to 0. And abracadabra, this assumes the value from this equation. So I will write T4 plus T4 minus 2 delta x minus 2 T5 is equal to 0. So 2 T4 minus 2 delta x minus 2 T5 is equal to 0. So simplifying a lot there, I can write T4 minus T5 is equal to delta x. And this is all because we simplified a lot of things. So now we have 4 variables, we have 4 equations. We can easily find them out, put them into the matrix, right? Put them into the matrix, and here we have the solution. So this is how you use the ghost point node. By introducing it and then eliminating it. So let me summarize the approach once again. So first, you see what flux has been given. Then you convert that into this expression. Second is you introduced a ghost point and apply central differencing scheme to this term so that you get an algebraic form. Third, you discretize the entire domain and then apply the central differencing scheme for the second order term. And fourth is you eliminate the ghost point altogether. After that, it's the regular procedure. Alright, so this is how ghost point can be applied. What are the alternate approaches? Alternatively, you can directly apply a forward difference or a backward difference scheme, and you can very well go ahead with that. For instance, in this case, instead of inventing a fictitious node, right, what you can in fact do is you can use or build up a relationship between T4 and T5 by using the logic. So T5 minus T4 or T4 minus T5, depending on the sign convention that you have adopted, and divided by delta x or 2 delta x, and that is how, and that is equal to whatever the value of q by k you get, that you can substitute and you can go ahead with that case. Now here you don't have to invent any other node, and in this case if you use the central differencing scheme or the forward difference backward difference approach, meaning without and with ghost point, for simple cases the results would be same, there would not be much difference. However, when we look at complicated cases and especially mixed boundary condition, and somewhere we have complex boundaries or the physics is complex, there they actually start to make real difference. It starts mattering which approach you take, and the ghost point method has seldom, or rather has often worked out to be the preferred one, because it is a very stable is a central differencing scheme, and it gives you accurate or near accurate answers. So as a new user, or as someone who is very new to CFD, it's good to understand the ghost point of FDM. And in fact, this ironically is the point which makes FDM a little cumbersome to use, because as we have seen in that video as well, finite difference method fails to handle complex geometries, and especially this ghost point method there, applying that in its true sense becomes again very challenging, and we are talking about really complex cases. So that's that. So this was a Neumann boundary condition. Let us talk about the third case, which is the Robin boundary condition. And by now you must have guessed how to deal with this, because this is going to be a combination of Dirichlet and Neumann boundary condition. So the idea here would be, if I have to represent in its simplest form, the idea here would be to equate the flux at the boundary, or let me simply write at the boundary, is equal to the convection or any other phenomena that is happening at the boundary. Meaning, this particular boundary condition represents an end which is exposed to the atmosphere, right? So for instance, in the case of Neumann, either you look at the case of a heat flux or insulation, Neumann very well captures these physics. If you talk about a convection boundary condition or a radiation boundary condition, again a simpler variation of it, Newton's law of cooling, that is perfectly handled by a Robin boundary condition. So if suppose we have a fin like this, which is the end is exposed to the atmosphere, and this fin is connected to some, like say, engine or a motor, Robin boundary condition captures the convection that is happening at the end perfectly well rather. And this is the representation of that case. At one end we have a Neumann boundary condition, at the other end we have a Dirichlet boundary condition. So that is that. Again, for handling this, you can use the ghost point approach. It will work perfectly fine. So as an assignment, I request you to do this and check whether the ghost point method and the forward difference, backward difference method were given the same answers. So it would be a fun exercise, and I request you to do it on your own, and let me know in the comments where you face difficulties. We may interact based on that. So as far as the boundary condition or the discussion on boundary condition is concerned, this is what I wanted to talk about. In the upcoming videos, I would then further start exploring about the schemes, the various mesh types, and a few other concepts. So slowly and steadily we'll start to increase the complexity a bit. But as far as the boundary condition goes, this was what I wanted to talk about. Thank you.